Welcome to Lecture 8, in which we will begin to discuss Chapter 3 of our text. But first I want to elaborate on a topic we discussed recently in class. If you will recall, we considered a situation similar to the following. We said, let V be a vector space. And then we considered I'll show. Let's let X and Y be subspaces of V. And we considered the following set. We considered the set of all vectors, maybe we'll call it V, the set of all vectors, little v, in the vector space, such that little v could be written as x plus y, where little x is an element of x, and little y is an element of y. Now, we called this the direct sum. We called this set the direct sum of x and y. However, if we're going to use that terminology, we need to throw in one more fact. So let's be a bit more precise now and say, let's first define the sum of x and y. And that is precisely the set that we have. It's the set of all vectors in V such that V can be written as x plus y, where x, little x, is an element of x, and little y is an element of y. And by the way, that is written as x plus y. Now, what about the direct sum? If the intersection of x and y consists only of the zero vector, remember that every subspace has to have the zero vector. You can see that easily from considering closure under scalar multiplication. So, if the intersection of the two sets consists only of the zero vector, then we call the sum a direct sum and use the notation x plus y. So I wanted to make you aware of that one extra requirement for this to be called a direct sum. Now, a couple of interesting notes. Note that even if the intersection of x and y is not just the zero vector, the set x plus y still makes sense and is in fact a subspace. In fact, that's what we showed in class. And now, just to clarify these ideas, okay, let's, and this is related to an example we saw in class, but we'll elaborate on it. So we're going to, maybe for our example, have v is equal to r3, and x is equal to the xy plane, and y equals the yz plane. Now, as we observed before when we looked at this example, the intersection of x and y in this case is the y-axis. Now, since this is more, since the intersection of x and y is more than just the zero vector, notice it does include the zero vector because, of course, the zero vector lies on the y-axis, but the intersection is more than just the zero vector. So since the intersection consists of more than just the y-axis, we don't call the set of all vectors that can be written as the sum of a vector in x and a vector in y the direct sum. We merely call it the sum. And so that's the set of all vectors v, in this case in R3, such that v is equal to x plus y, where x, since x is in the xy plane, that means that x could be written as alpha beta 0, and y, since y is in the yz plane, it could be written as 0 lambda gamma, where alpha, beta, lambda, and gamma are all real numbers. And of course, as we argued in class, when we add those two together, of course, we could simplify this and say x plus y is equal to the set of all vectors v in R3, such that v equals, we can go ahead and add these two vectors together, and we would get alpha beta plus lambda gamma, where alpha, beta, lambda, and gamma are real. But then if we look at that a little more closely, that's simply all of R3. Because any vector in R3 can be written as, keep in mind that if beta is real and lambda is real, then beta plus lambda is real. And so the set of all vectors that could be an arbitrary real number in the x component, an arbitrary real component in the y component, an arbitrary real number in the z component, well, that's just all of R3. So x plus y is equal to R3 in this case. But once again, we don't call this a direct sum of x and y. It's just a sum of x and y. Why? Because the intersection of x and y is more than just the zero vector. It consists of the entire y-axis. Now let's look at another example. So we'll call this example 1. And now in example 2, again we'll have v is equal to R3. And let's use the same x. So x is equal to the xy plane. And now we'll define z, which is the z axis. Now, X is a subspace of V, and I hope you can readily see that Z is a subspace of V as well, because if you take any vector that lies along the z-axis and add it to another vector that adds on the z-axis, you get a vector along the z-axis, so that proves closure under vector addition. And likewise, if you take any vector along the z-axis and multiply it by a scalar, you will still have a vector along the z-axis. So that proves closure under scalar multiplication. So again, we have two subspaces of V, just as we did in example 1, but the important distinction here is that in this case, the intersection of these two subspaces is just the set containing the zero vector. Here above, it was not just that set, but here it is. And so in this case, it is appropriate for us to call this the direct sum And of course, what we can say, since x is the xy plane, then an arbitrary vector in x could be written as alpha beta 0, and since z is the z-axis, an arbitrary vector there could be written as 0, 0, sigma. And of course, this then could be rewritten like this. And I should have included here alpha, beta, and sigma are real. And of course, then, as before, that just ends up being all of R3. But in this case, it is appropriate to use the direct sum notation because these two subspaces have an intersection that consists only of the zero vector. Now, one last thing I'd like to say here that it might be of interest to you before we move on into chapter 3 of your book is the following. The dimension of a sum is equal to the dimension of x plus the dimension of y minus the dimension of the intersection of x and y. This is a fact. I'm not attempting to prove this, but it's just a fact. And an example, if we apply that equation to example 1, this would say that the dimension of x plus y is equal to, and of course here I guess I should say, if x and y are subspaces of the same vector space V, then okay. And so in the first our first example, recall x was the xy plane, so its dimension is 2. Y was the yz plane, so its dimension was 2. The intersection of x and y was the y-axis, which has a dimension of 1. And so we get 2 plus 2 is 4, minus 1 is 3, is the dimension of x plus y. And indeed, that was exactly what we found. X plus y was equal to R3, which of course does have dimension 3. So you see that this checks out. Now notice, though, that in example 2, when we talk about a direct sum, and I'll go ahead and use z, so when we apply this same rule for a direct sum, because after all, a direct sum is a sum. It's a little more than a sum. Direct sum. When we use that terminology, direct sum, it tells us something additional about the sets. But a direct sum is a sum. So, so when we use this rule for direct sum, notice what we get: the dimension of x plus the dimension of z minus the dimension of the intersection of x and z. But in this case, when we have the direct sum, remember then that this will become, remember, if you have if x and z are subspaces, so in fact, let me go ahead and put x. Okay, so if x and z are subspaces of the same space, and it is appropriate to use the direct sum notation, then that means that their intersection consists only of the 0 vector. So we have dimension of the 0 vector. Now, what is the dimension of the 0 vector? The 0 vector is a vector space. You can check that it satisfies, it's a subspace of V. It satisfies closure under vector addition. It satisfies closure under scalar multiplication. So it is a vector space, but what is its dimension? Well, remember, the dimension of any subspace is equal to the number of vectors in its basis. Well, what is a basis for the space consisting only of 0? Well, you might think at first, well, a basis could have only one vector in it, and that's the 0 vector. But remember that the 0 vector can never be part of a basis, because the basis has to be linearly independent vectors. So the basis, in fact, is empty. The basis has no vectors in it at all, and therefore, since the basis has no vectors in it, and it has 0 vectors, then the dimension of the vector space is 0. So this becomes dimension of x plus dimension of z minus 0. And so we finally get that the dimension of the direct sum of x and z is the dimension of x plus the dimension of z. But again, we can only use that direct sum notation when x and z have an intersection that consists only of the 0 vector. And if you look at example 2, that works. In example 2, that says that the dimension of x direct sum with z is equal to the dimension of x. And remember, in example 2, x is equal to the xy plane, so the dimension of x is 2, and the dimension of z, well, z here is the z-axis, So since it's just the axis, the dimension of that is 1, and so we get 3, and sure enough, that is consistent with the fact that the direct sum of x and z is all of R3. So there is a little additional information about the sum of two subspaces and the direct sum of two subspaces. And just remember that the direct sum is a sum. However, we use it's a little bit more, and what it is that when we use the direct sum notation, it means that the two subspaces under consideration have an intersection consisting only of the 0 vector. So now that we've said this, we're interested in getting into chapter 3 of your book. And you'll see immediately why I wanted to be very careful about these definitions, because when you look in your book, you will see that the authors define the direct sum. This is the first item in your in chapter 3. They define the direct sum of vector spaces V and W to be the set of all vectors that can be written as a sum of a vector in V and a vector in W. In other words, even though your book is using the direct sum notation and is calling it a direct sum, they are not being careful to note, to say anything about the intersection of the two sets. Now, technically speaking, they probably should be careful about this, because after all, in their definition, they're just talking about vector spaces originally. But then we begin to immediately see that the vector spaces that they have in mind are state spaces. And once we see this, then of course we immediately see that if we consider these different spaces as state spaces, then we don't have to worry about these spaces overlapping with each other. What I mean by that, and before I even proceed, let me remind you again. In fact, let me break for just a moment, because I want to look up a link for you. Okay, I would recommend that all of you take a look at YouTube to at least be aware of the lecture series by Professor Susskind at Stanford. He has a number of different lecture series on YouTube on different topics, but one of the lecture series is on quantum entanglements. And if you look at lecture 2 in that series, you will see his description of how we can use electron spin as the physical representation corresponding to a qubit. And I think that is a useful idea for us to pursue in this chapter as we think about different vector spaces and taking either the sum or the tensor product of these vector spaces. You should keep in mind that the different vector spaces refer to different electrons. And therefore, once you get that idea in mind, then it's easy to see that the different vector spaces, even though they might have vectors that look, the way they're written, they look exactly alike, they're not the same vector, and these different vector spaces will not intersect with each other. And the particular lecture that I have in mind, the one where Professor Susskind discusses the idea of electron spin, where he introduces it, is here. Let me just read this out to make sure everybody can understand what I've written here. All this at the beginning is lowercase, https://youtube.com/watch ? And then this is a lowercase v, and then the equals sign, and then an uppercase V, lowercase t, uppercase b, uppercase r, uppercase k, lowercase w, and then the number 1, uppercase a, lowercase b, the number 7, and then uppercase e. I think that if you'll watch the first 30 minutes or so of that lecture, you might find it very interesting in it talks about measurement, and it talks about electron spin, and I think that you might find this very useful. I'd like to say just a little bit more about this before we proceed, and that's the following. Note that V equals, let's say, the set of all vectors A, B, C, D, such that A, B, C, and D are all real numbers, and where we have vector addition and scalar multiplication defined in the normal way, that is a vector space. Likewise, W, which is equal to the set of all 2 by 2 matrices, let's maybe call it alpha, beta, gamma, delta, such that alpha, beta, gamma, and delta are all real numbers. That, if we define matrix addition and scalar multiplication of a matrix in the normal way, then that is also a vector space. And in fact, we can talk about the sum or the tensor product of these two spaces. Let's just think about the sum for a moment. It's appropriate to call this a direct sum because these two vector spaces don't intersect with each other. They don't have anything in common because they don't even consist of the same thing. V consists of vectors, W consists of matrices, and so we can form a set and call it the direct sum of these two, but its elements cannot be reduced. Let me explain what I'm saying here. So I'll say note that 1, 2, -1, 7 I'm going to use that same notation, the plus sign with a circle around it, to denote the idea of adding together elements of different sets, which might not in some ways be compatible like this. So that plus 3.4 pi e 1.2. Now note that that's an element of V plus an element of W. So this is an element of the direct sum of the vector spaces V plus W. But that's all we can do. We can't somehow simplify this. We can't go ahead and add them any further to each other because these are just different objects. This is a vector from V, this is a vector from W, and notice now we're not saying that V and W are subspaces of some common vector space. No, V and W are different vector spaces, and in fact, in this case, it just doesn't make sense to try to do anything more with this. So this would be an element of V direct sum W. And that's just the way it is. So if we haven't, and so this is similar to the kind of idea we're talking about here, V and W. Now, we don't have a vector in a matrix. We have vectors in both V and W, but you need to keep in mind that in chapter 3, that the different vector spaces are referring to state spaces, and I would encourage you to think of it as the states of different electrons. So V might be the state space of electron 1, and W is the state space of electron 2. And so even though both of them might be the zero ket, you might pick the zero ket from space V and the zero ket from space W. Those are not really the same zero ket, because one refers to electron 1 being in the zero state, and the other one would refer to electron 2 being in the zero state. And so there's no way you could add them together to get just one ket. You would get a direct sum type of a ket. So it would be a situation similar to this. And we're really going to be concentrating primarily with the tensor product rather than the direct sum of vector spaces, but we have a similar kind of situation there. So let's, I think that as we proceed, this idea will become clearer. So this is all we'll say for right now on the direct sum. And so next we come to an idea that we will discuss at length, and that is the tensor product. Okay, I think the best way, certainly, for you to learn this topic, as is the case with any of the topics we'll discuss, is to read the material in the book, and then as I work through examples, I hope that will help to reinforce what the book has to say. And so when we start talking about the tensor product, I believe it's useful perhaps to help clarify some of these ideas for us to look at exercise 3.7a. We'll start with A. And in this problem, what we're supposed to do is to write 0, 0 in terms of the Bell basis. Now, what we should remember is that, what does this 0, 0 mean? Well, 0, 0 is a shorthand way of writing this. Is the tensor product of the zero ket in one state with the zero ket for another state. In other words, the first one is I would suggest that you think of that as electron 1. So 0 is the state of electron 1, and the electron 2 is also in the zero state. So, and if you had, of course, 3 numbers, then think of this as in a 3-electron system. But here we have 2 electrons, and the first one is in the zero state, the second one is in the zero state, and we want to write this in terms of the Bell basis. Now, let's look in your book and see what this Bell basis, what is that referring to? And the answer to this is on page 36. So from page 36, we have that the Bell basis is given by the following. We have phi plus, which is equal to 1 over square root of 2, 0, 0, plus 1, 1, phi minus, which is 1 over square root of 2, 0, 0, minus 1, 1, psi plus, which is 1 over square root of 2, 0, 1, plus 1, 0, and finally psi minus, which is 1 over square root of 2 times 0, 1 minus 1, 0. Now notice that these all refer to a 2-qubit system, and since the first qubit can have 2 values and the second qubit can have 2 values, then altogether we have the need for 4 vectors in this basis, because the dimension of the combined state will be 4. So let's see how we can solve this problem. Well, this is actually pretty easy, because if we note the following, so we want to write 0, 0 in terms of the Bell basis, so we could say 0, 0 is equal to A times phi plus B times phi minus plus C times C plus D times C minus. This is what we're actually being asked to do, is to write 0, 0 as a superposition of those 4 vectors, and then to find A, B, C, and D. Now, we know when we had a single qubit system, we were always talking about an orthonormal basis, and if we had an orthonormal basis, then it was very easy to find the coefficients in a case like this. For instance, if we wanted to find A, then we would pre-multiply both sides of this equation by the bra corresponding to the phi plus, and then by orthonormality all the other terms would drop out. This would be equal to 1, and so we would just have A is equal to the bra of phi plus with 0, 0. And likewise, if we wanted B, we would pre-multiply both sides by the bra of phi minus. But we have not yet confirmed that the Bell basis is orthonormal. So let's ask about that. Is the Bell basis orthonormal? We need to know that before we can use that procedure. Well, let's check this out. First of all, let's check, and I encourage you, well, but perhaps let me do the first one, the first couple, but then I encourage you to try to do the rest of them on your own. So let's take the inner product of a phi plus with itself. Okay, So when we do this, we will get, remember that, well, we're going to take, for the scalar part, when we take the dual, or the dual of a ket multiplied by a scalar, we want to take the complex conjugate of the scalar, and then the dual of the ket will be the corresponding bra. Well, so what we will have here is 1 over square root of 2 complex conjugate 0, 0 plus 1, 1. And then for phi plus itself, we have 1 over square root of 2, 0, 0 plus 1, 1. Now, the complex conjugate of 1 over square root of 2, since 1 over square root of 2 is real, is just 1 over square root of 2. So we have 1 over square root of 2, and then, of course, another 1 over square root of 2, so that will give us simply 1/2. And then we will get the following inner products. Now, how do we evaluate these? Because each of these is the inner product of 2 qubits with 2 qubits rather than 1 qubit with 1 qubit. And so what do we do here? Well, if it helps, you can write it out like this, maybe, to help you keep things straight. This first one is 0 direct product, tensor product, 0. Well, actually, let's just maybe do this in the following way. When you look in your book, you'll see the following. If you have AB inner product CD, this is equal to the inner product of A with C multiplied by the inner product of B with D. In other words, you take the inner product of the states corresponding to the first electron and multiply that by the inner product of the states corresponding to the second electron. So this becomes 0, 0 multiplied by 0, 0. The second one is 0, 1 multiplied by 0, 1. The next one is 1, 0 multiplied by 1, 0. And finally 1, 1 multiplied by 1, 1. And so this becomes 1/2 of 1 times 1 plus 0 times 0 plus this is 0 here, 0 times 0 plus 1 times 1, or 1/2 of 1 plus 0 plus 0 plus 1, or 1/2 of 2, which is indeed 1. So the inner product of phi plus with itself is 1. Now I will leave it to you to check that the inner product of phi minus with itself is also 1, the inner product of psi plus with itself is also 1, and the inner product of psi minus with itself is 1. And now let's check one of these with perhaps another one to make sure that the inner products of all these with each other are 0. Let's perhaps maybe take phi minus and psi plus. So phi minus, psi plus, well, phi minus will be 1 over square root of 2 0, 0, minus 1, 1. And again, if you want to be very careful, we'll put since we're writing the dual of it, we have the complex conjugate of 1 over square root of 2. And then for psi plus, we have 1 over square root of 2. And we will have 0, 1 plus 1, 0. And now we want to, or we're hoping, if this is an orthonormal set, then these should be orthogonal to each other, and we should get 0. So let's see if that's the way it turns out. Well, the 1 over square root of 2 conjugate, of course, is the same thing as 1 over square root of 2, and 1 over square root of 2 times 1 over square root of 2 will give us 1/2. So we get 1/2, and we will have 0, 0, 0, 1 plus 0, 0, 1, 0 minus 1, 1, 1, 0, excuse me, 0, 1 minus 1, 1, 1, 0. And now, using the rule that we just learned, this is the same thing as 0, 0, 0, 1. This is 0, 1, 0, 0, minus 1, 0, 1, 1, and minus 1, 1, 1, 0. And again, just to make sure you follow that, we take the first numbers. These are the states of the first electron, so we take those inner product with each other, and then 0 and 1 for the second electron down here. 0 and 1 for the first electron, 0 and 0 for the second electron. 1 and 0 for the first electron, 1 and 1 for the second electron, and finally 1 and 1 for the first electron, 1 and 0 for the second electron. And now let's simplify this. Well, we know that 0 inner product with itself is 1, but the inner product of 0 and 1, those are orthogonal vectors, so we get 0 and 0 times 1 minus 0 times 1 minus 1 times 0. And this is indeed equal to 0. And you could check all of the other possibilities as well. and you will find out then that the Bell basis is indeed orthonormal. So now that we know that the Bell basis is orthonormal, we can go back to our original problem, which was to express 0, 0 in terms of the Bell basis. So again, we had 0, 0 is equal to A times phi plus B times phi minus plus C times C plus D times C minus. Just as we had right here. And now that you know that the Bell basis is orthonormal, I hope that you know right away how to find A, B, C, and D. We've already mentioned it once, so I hope that you understand that, and I'd strongly recommend now that you stop the video and try to find A, B, C, and D, and then once you think you have the answers, turn the video back on and check your work. Okay. So we know, since the Bell basis is orthonormal, that A will be equal to phi plus 0, 0. B equals phi minus 0, 0. C equals C plus 0, 0. And finally, D equals C minus 0, 0. So let's go ahead and compute each one of these. A then will be equal to 1 over square root of 2 conjugate. Zero, 0 plus 1, 1. And here we have on the right hand side we have 0, 0. So this is equal to 1. Of course, the complex conjugate of 1 over square root of 2 is just 1 over square root of 2. And we'll have 0, 0, 0, 0 plus 1, 1, 0, 0. And that is equal to 1 over square root of 2 times 0, 0, 0, 0 plus 1, 0, 1, 0, and that will be equal to 1 over square root of 2 times 1 times 1 plus 0 times 0, which is 1 over the square root of 2. So A is equal to 1 over square root of 2. Now, even if you had trouble before, I hope that now, having seen that example, you see what you want to do, and you can find B, C, and D. So if you had trouble before and you didn't find B, C, and D then, please stop the video now, try to find them, and then resume. Okay, so for B, we have 1 over square root of 2 complex conjugate, and now we're looking at V minus. So we have 0, 0, minus 1, 1, and then 0, 0 on the right. And again, the complex conjugate of 1 over square root of 2 is 1 over square root of 2, and we will get 0, 0, 0, 0, and this time minus 1, 1, 0, 0. And this time I won't show quite so many details. We can see that this is equal to 1 over square root of 2. So B, like A, B is equal to 1 over square root of 2. And now for C, C is equal to the complex conjugate of 1 over square root of 2 times 0, 1 plus 1, 0, and then 0, 0 on the right. And this is, as usual, the complex conjugate of 1 over square root of 2 is just 1 over square root of 2. And now in the parentheses, we will have 0, 1, 0, 0, plus 1, 0, 0, 0. And that is 1 over square root of 2 times 0, 0, 1, 0, plus 1, 0, 0, 0. And we see that this is 1, but that is 0, this is 0, and that's 1. So this is overall 0. C equals 0. And finally, D, the work is essentially exactly the same, and D will be equal to 0. And so what we find is that 0, 0 is 1 over square root of 2 phi plus 1 over square root of 2 phi minus. This is the answer to this exercise, and let's just check it to make sure. So I'll put a question mark or the equal sign. We get 1 over square root of 2. Now remember that phi plus is equal to 1 over the square root of 2 times 0, 0 plus 1, 1. And then we have 1 over square root of 2 times phi minus. And phi minus is 1 over square root of 2 times 0, 0 minus 1, 1. So does this work? Well, we have 1 over square root of 2 times 1 over square root of 2. So 1/2 times 0, 0 plus 1, 1 plus 1/2 times 0, 0 minus 1, 1. And this is 1/2 well, it's easy to see here, I think, that this does work out because the 1 terms will drop out because this one's preceded by plus and this one's preceded by minus. But the 0, 0 terms will combine. We have 1/2 and 1/2. And so, indeed, in the end, we get 1 times 0, 0. And so, sure enough, that works. And so, since the Bell basis is an orthonormal basis, it is very easy to find the coefficients. And that gives us an introduction to Chapter 3. And since that's an hour now, I think it's a good time to stop. So now I'll give you some problems, some very simple problems, and we will then, you'll begin working on Chapter 3. I don't think it will take us very long to get through this chapter, but we do want to make sure we understand what it has to say. So for the problems for Lecture 8, we'll just have two relatively straightforward problems. What is plus minus in terms of the Bell basis? And you have these choices. And what is minus plus in terms of the Bell basis? And the same choices. And 8.3 will be given in class. And just to make sure you understand these choices, in each case we have the phi plus ket, here's the phi minus ket, psi plus, psi minus, and I believe everything here is fairly legible. So that's it for the problems for Lecture 8, and good luck.